The paper that we, Group 6, are reviewing is titled Morpheus Towards Automated SLOs for Enterprise Clusters. And motivation for creating Morpheus. First part of it has to do with the high cluster utilization versus job performance predictability. Morpheus addresses the tension between these two by codifying user expectations, enforcing SLOs with novel scheduling techniques, mitigating performance variance through dynamic reprovisioning. And when it comes to codifying user expectations, Morpheus aims to make implicit user expectations explicit by codifying them as service level objectives, or SLOs. And these SLOs are derived from historical data reflecting the past performance characteristics of jobs. For enforcing SLOs with novel scheduling techniques, the system employs novel scheduling techniques to enforce the SLOs. This includes isolating jobs from sharing induced performance variability, meaning that the performance of one job is not negatively impacted by the activities of other jobs sharing the same resources. And as far as mitigating performance variance through dynamic reprovisioning, Morpheus addresses inherent performance variance, such as that caused by failures, through dynamic reprovisioning of jobs, which we'll go into more detail later. And this involves adjusting resources allocated to jobs in real time to mitigate the impact of unforeseen events. And some of the main motivations involve cluster workloads, predictability challenges, and changing conditions. So the first part would be cluster workloads, which is quoted in the paper. Proper execution of production jobs is crucial. Predictability trumps fairness, and production jobs are often periodic. And as far as proper execution of production jobs is crucial goes, it means that the majority of the work done on these clusters is for important production jobs, making it more than 75% of the workload. And users are mostly concerned with ensuring that these production jobs run smoothly and on time. For predictability trumps fairness, it essentially means knowing how long jobs will take to complete is more important to users than fairness when it comes to resource allocation. And production jobs are often periodic, means that they run regularly on a schedule, often handling continuously arriving data. And for predictability challenges, it is said in the paper that manual tuning of job allocation is hard, sources of performance variance. Manual tuning of job allocation is hard means that users find it challenging to manually allocate the right amount of resources for their jobs. Many jobs are over-provisioned, meaning that they get more resources than they actually need. And a study shows that 75% of jobs are over-provisioned, some are over 10 times more than necessary. And sources of performance variance means that there's a correlation between resource sharing and job runtime variance. Even in controlled experiments, they observed that job runtimes remain unpredictable due to factors like slower tasks. For changing conditions, in the paper, it mentions that cluster conditions keep evolving and jobs may run on different server types and user scripts keep evolving. And for cluster conditions that keep evolving and jobs may run on different server types means that different types of machines are used, like stock keeping units, SKUs, and this hardware variation can affect job runtimes. User scripts keep evolving means that the instructions for running jobs evolve with changes in code structure happening quite frequently. And is the motivation sound? And while the motivation highlights the importance of predictability for users, it'd be valuable to understand the perspectives of a diverse set of users. So different users might have varied expectations and requirements, and the system should consider these. And the motivation behind Morpheus emphasizes predictability over fairness when it comes to resource allocation. And like mentioned before, while it may align with user priorities, there could be some groups or some users where fairness is also equally crucial. And balancing these priorities is a complex task and might not always work. And just because something works in theory or in controlled environments does not mean it will work in the real world, where there are numerous outside factors that could affect the system from functioning properly. And this motivation also mentions a user study and doesn't delve too extensively into how the users have been involved in shaping the solution, though we will go into a case study later. Though it ensures that the solution aligns with user expectations and is user-friendly, and ensures that it's viral for its success. And now into the design main idea behind Morpheus. There are several key components for it, which include automatic interference module, which has some categories of extractor of target SLOs and job resource model, a reservation placement, and dynamic reprovisioning. And essentially, the extractor of target SLOs analyzes the provenance graph, which is right over down at the bottom left, to derive deadlines statistically. The job resource model processes telemetry information to construct a tight envelope around typical job behavior. And reservation placement expresses SLO and job resource model in recurring reservation requests. And it utilizes the low-cost algorithm, which we'll go into more detail in a bit, which is specialized for periodic jobs to efficiently allocate resources. And dynamic reprovisioning monitors job progress and adjusts the reservation dynamically to cope with inherent unpredictability. So, before we go into detail, how does Morpheus work? Essentially, the first part is job submission. Users submit periodic jobs with manually provisioned resources. Group 2 captures data. Provenance graph is one part of that, which captures data dependencies and different operations. And there's also telemetry history, which records resource utilization of each run. And then there's SLO inference, which drives a deadline SLO from the provenance graph. And it derives the job resource model from the telemetry history, representing resource demand over time. Then the fourth step is user sign-off, where users sign off or override the automatically generated SLO and job resource model. Then step 5 is reservation enforcement, which adds a recurring reservation for the job to the cluster agenda based on the job resource model. And new job instances run within dedicated resources provided by the recurring reservation. Step 6 is dynamic reprovisioning, which monitors job progress online and adjusts the reservation dynamically to mitigate inherent execution variability. And number 7 is continuous learning. Morpheus feeds back the provenance graph and telemetry information of new runs for continuous refinement of the SLO and job resource model, so it can develop and learn. And there are several limitations of Morpheus, however, which include control over globally shared resources, support of non-periodic jobs, and automatic SLAs, which is, I'll go into details. So control over globally shared resources. Morpheus can enforce decisions only at the container level, so it lacks control over globally shared resources like bandwidth on switches. And their support of non-periodic jobs. While supporting both periodic and non-periodic reservations, it does not automate SLO and job resource model extraction for never-seen-before jobs, or jobs it doesn't recognize. For automatic SLAs, Morpheus contributes to automatic SLAs, but it does not aim at providing a comprehensive automated SLA, which involves different business, economic aspects that are beyond the scope of what the paper details. And now that we're going into detail, let's start with one of the first key components, the automatic interference module, and the subcomponent, the extractor of target SLOs. So as you can see, it mentions the provenance graph, which involves reasoning about cluster data, which you can see at the bottom right there. And essentially, there are multiple parts to each of these. So for the provenance graph, there's semantic graph representation. It utilizes as more of a primary inference tool, and it captures logs, including job execution details, file system accesses, system metrics, and it basically represents it in a nice graph. There's also isolating periodic jobs, and individual job instances are essentially grouped into periodic jobs based on criteria, like exact matches of different job names, approximate matches of source code signatures, and different near constant arrival times. Then there's estimating SLOs from the provenance graph. So basically, the component derives estimates for the earliest start time and the deadline for a periodic job, which places emphasis on actionable deadlines, ensuring that there is significant flexibility in job execution timing. Then the second part of the automatic interference module is the job resource model, which has several different components to it, such as overallocation penalty, which is the average overallocation of containers, and underallocation penalty is essentially a penalty which captures the eventual underallocation of resources. So essentially, they allow the job to catch up, quote unquote, on underallocations using resources available later in the run. And the last time step is the average debt. And there's avoiding lazy solutions. So just focusing on optimizing the above parts to it can lead to solutions that under provision initially and compensate by aggressively allocating towards the end of a job's execution. So the paper mentions that they have to sustain the average normalized instantaneous underallocation below a specified threshold. Then there's complexity, and since it's way below the computational limit of top solvers, they obtain a solution within a few seconds for all periodic jobs in the clusters. Assuming that if it was above the computational limit, it would happen in less than a few seconds, maybe less than a second. Then there's estimating parallelism. We assume that the skylines that they mention are generated under capacity allocations and are sufficient enough to satisfy maximum parallelism. Satisfying the maximum parallelism a job instance can harness. And this assumption holds true for production jobs because they are typically overallocated to meet their deadlines. And now there is reservation placement, which involves the low-cost algorithm, which we mentioned before. And the algorithm is used to pack multiple periodic jobs and involves periodic reservations, problem formulation, and packing with this algorithm, which go into more detail in the next several slides. And it essentially expresses SLO and job resource model in recurring reservation requests and utilizes a packing algorithm, an online packing algorithm that is specialized for periodic jobs to allocate resources. When it comes to periodic reservations, essentially time slots are reserved for periodic jobs, and the importance of them is that they ensure timely execution of crucial jobs, And some characteristics of it are predefined duration, recurrence, and priority. Predefined duration is allocated based on the job's needs, and it occurs at regular intervals, often higher than non-periodic jobs due to their repetitive nature. And the problem formulation is another part of it. So there's setting, objective, and constraints, and requirements. So for the setting, it involves online job revealing, and that's essentially input that comprises of a set of periodic jobs revealed to the system one by one in an online fashion. And so that essentially aligns with what Morpheus aims to do, where the periodic jobs are introduced dynamically over time. And there's essentially also a time range with the least common multiple period, which ensures that it aligns with patterns that Morpheus has already identified in the past, so that it knows how to essentially reserve resources efficiently. Then there's objective and constraints, which involves allocation goals, balanced cluster load, and not rescheduling existing jobs, and contingent allocation. So allocation goals essentially involve primary objectives of the algorithm, which are to allocate containers to periodic jobs and meet requirements by the deadline, as well as minimize waiting time for non-periodic jobs. The balanced load cluster essentially aims for a balanced cluster load over time, so it increases the likelihood of accommodating future jobs, which is consistent with Morpheus's goal of efficient resource utilization. And when it comes to the not rescheduling existing jobs and contingent allocation, essentially not rescheduling existing jobs is pretty self-explanatory, but the entire allocation must be contingent, so there's no holes, quote unquote, that are allowed in the allocation, essentially. Then the requirements involve kind of like an online scheduling challenge, which is basically a problem at the moment that is challenging for single stage jobs, and the complexity is recognized by Morpheus and by the people who wrote the Morpheus solution, which shows how intricate and difficult dynamically managing periodic jobs is, and more of a preference for lighter solutions. And while the offline version would be cast as like a mixed integer linear problem, and Morpheus opts more for a quicker and lighter solution in terms of running complexity due to its dynamic nature. And there's also incremental solutions to maintain steady reservations for existing jobs, adapting only to substantial changes in resource demand. And next problem is packing with low cost, which essentially involves the basic algorithm of it, multiple instances, and non-periodic job. So to go more into detail, the basic algorithm of low cost, which is sort of like the basis for Morpheus, is that it follows a greedy procedure, which means that it iteratively places containers in a cost-efficient manner, and it handles stages of jobs in reverse chronological order. And also, it prioritizes minimum cost allocation, so it repeats the procedure for different endpoints and selects the allocation with the minimum cost, which is very important in the real world. And there are multiple instances of it, such as how it aligns with the least common multiple, and all instances with the same offset to the period of the last job, or to the period of the job. Then there's cost calculation. So for each time step within the job's period, the cost is determined as the maximum cost across all time steps with the same offset. so it ensures consistency. And there's also competitive ratio, which is under the assumption that periodic jobs have the same skyline requirement but differ in their period. And as far as the non-periodic job goes, essentially Morpheus does prioritize periodic jobs over non-periodic jobs due to the fact that it's very difficult to dynamically allocate resources, and it's just a lot easier in the long run. And when allocating resources for a new periodic job, Morpheus gives priority to the periodic jobs, as we mentioned, and ignores most scheduled non-periodic jobs. And resources for non-periodic jobs are only reallocated if needed, which kind of uses the logic similar to the low-cost algorithm, but not exactly that algorithm. Then we move on to dynamic reprovisioning. So that involves the dynamic reprovisioning algorithm, or DRA, and adjusts low cost to facilitate reprovisioning, as you can see in the example in the figure below. So the DRA, or the dynamic reprovisioning algorithm, has several components to it. So the reprovisioning is essentially triggered when a job's resource demand exceeds the allocated resources in the reservation skyline. And it stretches that skyline of resources to accommodate a slower than expected job execution if need be, which is why it's dynamic. If it was static, it wouldn't be able to do that. And extra resources are granted for up to a specified duration, which is by default 1 minute, based on the job's instantaneous demand. Though there are limitations because the amount of resources can be capped at a certain point, ensuring that the job does not receive more resources than it requests. And the implementation of that is that DRA updates the current instance of the periodic reservation by invoking the low-cost algorithm, which ensures the update is accepted only if sufficient resources exist in the plan. So when it comes to low cost, or adjusting low cost to facilitate reprovisioning, that involves essentially the fact that the success of the dynamic reprovisioning depends on the position of the original reservation allocation with respect to the algorithm. And the trade-off exists between allocating resources far from the deadline, so it allows time for reprovisioning, and placing the allocation close to the deadline, so it ensures data availability. So it has to come to a sort of compromise or a trade-off. And low-cost cost function is adjusted for problematic jobs with high variance by adding an alignment penalty. The penalty is literally proportional to the absolute time distance between the midpoint of the allocation and the midpoint between the start time and the deadline of the job. And the objective of this penalty incentivizes allocations that strike a balance, avoiding being too close to either the start or the deadline of the job. And now, you can go.
Thank you, Staples. Now we are seeing the Morpheus versus traditional methods. Traditional, in that we can see like manual turning, static resources allocation, and less adaptive to changing conditions. Uh, when we see to the Morpheus, there is a dynamic resource allocation. User centric is like focused on users' expectations and needs, and we'll see the adapter in this we can the Morpheus, we can use the adaptable to evolving cluster conditions. Let's go to benefits of Morpheus. Here we are seeing that predictability, efficiency, user satisfaction, and scalability. Predictability is like improved job performance predictability, and efficiency, it's like we can see the optimal resources usage due to dynamic improvisation. And we see the user satisfaction. In that, we can see like by ensuring SLOs or MET for user satisfaction. In scalability is like adaptable to different sizes of clusters. Below, we can see the comparisons of Morpheus with current user manual provisioning, like SLO extraction, how the graph is there, and job provisioning, and SLO violation reduction, and cluster size. We can see the graph, how it is going. Now we are going to Morpheus in practice. There are three, like user feedback loop. It, it is like continuous engagement with user to improve SLO interfaces. And in the real world performance, we can use like we can maintain performance even in complex enterprises cluster as well. In adapting to changes, like we can do like quickly, we can adjust to evolving user scripts and changing cluster conditions. Now we are going to see future improvements for Morpheus. We can look to the graph, and here there is like we can take like handling non-periodic jobs. Further enhancement to support the tasks, we can use this. And for the intercluster coordination, we can use like ensuring SLOs or MET even in interconnected clusters. For improved user feedback mechanism, we can use for better and quicker SLO adaptation, we can use this. And we can move to the case study with Morpheus. For this, we can do enterprises. For example, enterprises X, we can see the 20% of increase in resource efficiency. In tech companies, we can see like improved predictability, like 15%. In financial institution, we can see like the reduced manual turning effort by 40%. There are three different case studies we can see in Morpheus. And then we can move forward to the implementation details for Morpheus.
Yes, thank you. So the
Yeah.
implementation of Morpheus is built as an extension of Apache's Hadoop and Yarn. And the system consists of three main components, which include the automatic inference engine, the reservation placement component, and the dynamic reprovisioning mechanism, which we went into extensive detail with before. So just to mention again, the automatic inference engine is implemented as a standalone service where it continuously receives information about the origin and history of data and telemetry data about the performance of the system data. It also submits reservation requests to the resource manager of Yarn via its REST endpoint. The reservation placement component implements low cost, which is the algorithm that is used to pack multiple periodic jobs as an in-process functionality of the resource manager. The dynamic reprovisioning mechanism is implemented as a monitoring thread in the resource manager that observes job resource requests and triggers resizing of reservations based on dynamic conditions. There are several issues with this implementation, which involve mainly scalability and cold start handling. Now, when it comes to scalability, Morpheus uses periodic reservations instantiated as per job queues in the resource manager, though challenges arise with Yarn's resource manager scheduler, which is designed for a small number of infrequently reconfigured queues. And scalability is addressed by reworking the resource manager scheduler locking mechanisms, which introduces a finer granularity, locking, and lock-free data structures. And the changes allow Morpheus to achieve scalability orders of magnitudes higher than the baseline. And when it comes to cold start handling, essentially those are where historical data is not available, like for non-recurring jobs or initial runs of a new recurring job are addressed. Basically, there are three lines of defense to deal with this problem that the paper mentions, which include backwards compatibility, where Morpheus can support running jobs with existing fair queuing infrastructure, manual SLOs and job models, where users can manually define SLOs and job resource models for both periodic and non-periodic jobs, and application-specific tools, which are for fixed application frameworks like Hive, Giraffe, Scope, Spark, which are the frameworks that the paper mentions. They're tools that can be built to predict behavior using sample runs and modeling. And there's also integration with tools like Predict for Giraffe computations and Perforator for Hive, Tez, MapReduce is mentioned, but complete integration has not been achieved yet, so that's part of the issue. And now into the evaluation of Morpheus. So essentially, when it comes to performance on the enterprise trace, there is SLO representation, where Morpheus successfully represents SLOs for over 70% of periodic jobs in the enterprise trace, showing that the system can derive sensible SLOs. This is shown in the graph. There is SLO attainment, where Morpheus achieves high SLO attainment gains over the baseline, leveraging job slack and demonstrating its ability to pack reservations efficiently without increasing cluster cost. There is parameter tuning, where fine-tuning parameters influences the balance between the tight skyline fitting and the likelihood of SLO misses, with a value of 1% yielding the best results. And packing efficiency, which involves Morpheus's packing algorithms like low cost, where they can handle complex skylines, efficiently utilizing Slack and SLOs to densely pack the cluster agenda while achieving high utilization. And now into a breakdown of contributions. Morpheus's static techniques, including SLO extraction, packing, and job resource modeling, contribute to a significant reduction in baseline cluster size. Then the dynamic reprovisioning mechanism further allows a trade-off between user utilization levels and SLO attainment, demonstrating the importance of each technique in achieving overall improvements, which can be shown in the figure below. Now there's physical deployments and scale tests, which involve adversarial workload, where Morpheus successfully protects jobs from adversarial workflows, eliminating sharing-induced variability and dynamically reprovisioning to meet SLOs even under intense stress. And as you can see below, there's a scale test run on 2,700 nodes, where it shows that Morpheus demonstrates scalability by running on a 2,700 node cluster, which is pretty high, sustaining a high load and achieving high plan utilization and maintaining user-facing latencies within expectations. Then there's the production deployment on 4,000 nodes. And in a production environment, Morpheus controls runtime variability for periodic jobs, showcasing its effectiveness even when dealing with a combination of periodic and non-periodic workloads. And with that, is Morpheus worthwhile? So the paper claims that Morpheus enables predictable performance with less resource provisioning, which is a win-win for operators and users. But is it really a win-win solution? So Morpheus appears to be a sound solution for addressing challenges related to resource allocation and job scheduling in a cluster computing environment, though it's essential to consider the specific requirements and use cases of a given cluster computing environment. So honestly, further evaluation testing in a real-world scenario would be necessary to validate the effectiveness of Morpheus in specific contexts. So essentially, bringing theory to practice, and then we can conclude whether Morpheus is really a worthwhile solution. And that's all. Thank you.